Good morning, afternoon, or evening, depending on when you're watching this, and welcome CTM students to lesson 8.2 can be found on these pages. And you've got some new vocabulary here, or some stuff that we just need to know. Some of it may be review from our previous lesson, some of it may be brand new words for you, or review from another math class. And as always, using your extra examples in the book. I'm doing different examples from what's in the book, but there are some very similar ones in the book to what you see here as well. So let's get started. Alright, so last spring break, I had a chance to go to Hawaii for the first time, and it was spectacular. It was amazing. And these are not pictures that I took, but I have some similar pictures to these. But I saw some signs like this, and I saw some signs like this in Hawaii, especially on the island of Kauai, which is this one right here. I had the chance to do some island hopping and went to the 5 largest islands in the islands of Hawaii. So we have the big island of Hawaii, Maui, Molokai, Oahu, and Kauai. And saw some things like this. I want to just use that to help me describe just a couple quick things here. So write this down as your title. Put a heading of length to begin with, and then just some quick things, some length conversions that you should know. So these are 2 things I expect you to have memorized. These 2 length conversions. So 1 mile, if you're ever traveling in a foreign country, you'll probably see signs like this without the mileage on them. You'll see the kilometer distances instead. So we have to know how to convert from this to this. 1 mile is about 1.6 kilometers. If you look at this mile marker over here, I think I even remember seeing this sign. This one was on the island, the big island of Hawaii, just a little north of the city of Hilo, which is right over here-ish, and so a little around that way. If you take 1.6 and multiply it by 5, you get about 8, and so you do get 8, actually. And so this is an approximation, 1 mile, about 1.6 kilometers. And then 1 inch, this is another one that I need to have you memorize. 1 inch is about 2.54 centimeters. These are very close approximations, so very good approximations here. If you're using these conversions, you're going to get a very good, reasonable estimate for what you're looking for. So let me bring this up a second. There's a conversion calculator here. So let's say you were trying to find even more precisely what something was. If you entered something like this, let's say, well, that sign said 8 kilometers, 5 miles. So let's see exactly more precisely what this is. So 5 miles, there we go, 2 kilometers. You can find a lot of conversion things on the internet like this. I just found one of the top ones that came up, and it says 8.04672 kilometers. So very, very close to 8 kilometers. We look back at what we had right there, and that seems to match up pretty well then, right there. And then I remember going past these, and I saw this stuff. Oh my gosh! So Princeville, Hanalei, beautiful coastline here. And then if you keep going and driving around the north side of Kauai, which is this island right here, you can hike along the coast here. Whoa! That was one of my favorite day hikes I've ever done. Incredible hiking on the island of Kauai, and all the islands, but especially Kauai. That was one of my favorite places, probably my favorite island that I visited. I didn't get to spend as much time on Maui because I wanted to. The big island was pretty sweet too. Oahu is a little more built up, you might say, so lots of buildings and stuff. If you like the tourist type stuff, Oahu is definitely a great place to go. So let's check out example 1. So let's determine. Write this down for me. Example 1. Make sure you're writing the numbers with the examples too. That just makes it a lot easier for me to check and see that you got everything for the full points. So determine what's most appropriate to measure. And we'll do a few different things here. You can see my pictures are going to match up with what I put here. So let's say the width of a book. Maybe you like to read books. I know I do. Here's a little bookworm. Maybe you're a bookworm. You like to read books. Sometimes those people are called bookworms. So the width would be this part right here. I would think of this probably being the length. In this case, this would be the width. What would be most appropriate? So I've brought up 8.1 right here, and thinking of these prefixes, remember. So would a millimeter be most appropriate? A centimeter, a decimeter, a meter itself, deca, hecto, or kilometer, kilometer. Definitely not going to be measuring a width of a book in kilometers. I think what would be most appropriate for this would be centimeters. So I'm going to put centimeters next to that, box that in. So centimeters I think would be most appropriate. If we were using English, or the US customary, I should say, measurements, I'd probably say inches instead. Millimeters maybe, but centimeters I think would be most appropriate. B, what about your wingspan? What am I? I'm just spelling span right there. Your wingspan. What is a wingspan? If you don't know, wingspan is like this. This is Anthony Davis, an up-and-coming, I think, superstar in the NBA basketball, being my favorite sport. This guy has a 6'10" wings, or 6'10" height, but he has a 7'4" wingspan, so he can actually reach farther than his height. Generally, it's considered pretty normal to have a wingspan equal to your height, but this guy got blessed with, you might say, long arms, so he can block shots even better than if he was just 6'10" wingspan. So wingspan, 6'10", that's in English. I think the best way to measure that would be either meters or centimeters. Your height you're going to measure in meters or centimeters most of the time. Your wingspan will be measured in the same way. So choice, or part C, how about the length of a fly? So a common house fly like this little guy over here. A centimeter would probably be too big actually, or it might just be exactly 1 centimeter. So we'd want to be a little more precise on that. For this one I would say a millimeter would probably be the best thing to use. So a millimeter would be best. How about the distance from LA, Los Angeles, to Seattle? So you can see that over here on the map. So here's LA. Looks like making a stop in San Francisco and then going to Seattle right there. What would be the best way to measure that? Measure that using metric units. So miles, I would say, in U.S. customary system, but kilometers is most appropriate in this case. You don't want to measure this in meters, or definitely not in millimeters. It's going to be a very long distance, so kilometers I think is most appropriate there. And this is Tuba City, Arizona, their water tower. How about this? The diameter of a water tower. So to me, kilometer would be much too big for that. Millimeter too small. Centimeter I think too small as well. I think what would be most appropriate would be meters instead. And let me plug in my computer. It looks like my battery's running low. Alright, I think the screen might have just gotten brighter too, so we're all plugged in now, ready to continue. So let's check this out. How about this next? So I want you to put a title heading just like you did before for length. Now we're doing a big title heading for area. So this is our next big thing to talk about. We're talking about length, area, and volume in this section, or in this lesson. So area, what is it first of all? Let's give a kind of a just informal definition. It would be the space enclosed by an object in 2 dimensions. So 2 dimensions. A length is just a 1-dimensional measurement. Area is a 2-dimensional measurement. So in 2 dimensions. And what are we going to use for this? Oops. Because it's in 2 dimensions, we're going to use square units. I'm going to use square units. And I wanted to mention one other thing with this one. As always, using the extra examples in your book, but if you look at example 1 specifically in your book, not this example 1, but in your book, on pages 440 to 441, you can see 10 others. So if you're struggling with this, you're like, this still isn't quite making sense to me, look at those ones on those 2 pages, 440, 441, and get 10 other ones there that you can look at. But for this, I want to remind you of something. In your syllabus, this is a zoomed in section of your syllabus for the required class materials. You're supposed to have this. I'll put a little asterisk next to that because a ruler will be provided for you in class, but you need one for your own to use at home. So you're watching this right now at home, or maybe at a friend's house or relative's house, maybe at the library, or maybe at school. It's got to include measurements for both inches and centimeters. If you're watching at school, you can come and borrow a ruler from me. If you're watching at home, it's got to have that. So we should have that. Go get that right now if you need to. Pause the video. Go get that right now if you need to. And then come back to this. Okay, so hopefully you have your ruler now. And I've got my ruler right here too. And I'm going to not do that. There we go. I'm going to move this over. You'll notice this right now is in top scale is in millimeters. If I change it to centimeters, there's 10 millimeters, remember, in 1 centimeter. So I'm going to just keep it with millimeters. We'll just remember that from here to here, that's going to be 1 centimeter. 10 millimeters is 1 centimeter. So this I'm going to, and the bottom scale is in inches right now. You may have a ruler similar to that. So I'm going to draw a line here. Oh, look at that. That's sweet. I didn't even know that it would draw like that. Ooh, fancy. And I'm going to take this now. I want to rotate it the other way, actually. Let's see if I'll do it this way. Let's see. There we go. Well, that'll work. All right, and I'm gonna make this one to scale. So I'm drawing this one very carefully. I want you to do the same thing there. Okay, so now I got that. I'm gonna rotate it again. Like that. All right. I'm gonna do. There we go. 1 centimeter again, like that, and rotate it one more time. If I can, come on, there you are. I'll bring this back over here, rotate just a little bit more. I think that's good. Yep. Okay. And draw that. Let me see if I can move that over just a smidge more. It seems to want to go right to there. So let's see. Okay, so that's pretty close. That's pretty darn accurate, I would say. This was 1 centimeter by 1 centimeter when we drew that. Now I want you to draw something that's 2 centimeters by 2 centimeters. So take your ruler, do the same sort of thing that we just did there, but make it 2 centimeters by 2 centimeters. So this, I'm going to take this, not that far, there we go. And turn this. I can turn it just a little too far there. Come on, there. Oh, no, no. Honestly, I'd rather have just a normal ruler right now, but this will have to do. Okay, there we go. And remember, 2 centimeters for this one. So if I went from 13 to 15, that would be 2. I just subtract those. And let's see, I'll move this way now. I can get that straight horizontal as best I can. That looks good. Line it up with 0. Move it up just a little bit there. And now I'll draw that. And then finally, do this. We won't draw in scale or perfectly to scale too much, but this is definitely one of those times where I want you to do that. So that is pretty good for that. I know these aren't touching perfectly, but I'm going to call that good with the tool I've got. So this was 2 centimeters by 2 centimeters. You should have the same sort of thing drawn on your paper. And what's the area of this? The area of this is 1 centimeter squared, a square units there. So this is 1 centimeter squared. This one's 2 by 2 though, so this one's 4 centimeters squared. So I want you to notice something with this. Notice I increased the length, the lengths by 2, but the area increased by 2 times 2. The area increased by 4. So that's an important thing to note. If you increase all the lengths in a certain way, the area will increase by even more. So it's more than just 2 times bigger. So 2 times, let's write this off to the side, 2 times bigger sides means 4 times bigger areas. 2 times bigger size means 4 times bigger areas. Oops. There we go. Alright. And so then down here, let's put US customary. And then over here we'll put metric, the metric alternative. We're used to in the US customary system. That's just what we've used all our lives. But I want to get used to the metric alternatives here, and hopefully I hope, crossing my fingers here, I want this to be what eventually takes over in the US, so we can be like the rest of the world and have things that make more sense mathematically, and just, yeah, it's just so much easier once you understand the metric system to use the metric system. So the metric alternative is centimeters squared. That's a little smaller because an inch is bigger than a centimeter, but centimeters squared is a similar sort of measurement. That's what you'd use for relatively small things. You could say feet squared or yards squared in US customary system. That would generally match up with something in meters squared in metric, in the metric system. So you could also have something like miles squared. You could call that something kilometers squared. So miles squared is bigger than a kilometer squared because a mile is bigger than a kilometer, but these units would be used to compare similar things. And then an acre is also a common unit of measurement for area in the US, and this is, remember, we're leaving spaces instead of putting commas between the 3 in this chapter. So 43,560 feet squared is what 1 acre is. A similar type of measurement in the metric system is called a hectare, and it is abbreviated with an HA, and it equals 100 meters times 100 meters, or in other words, that's the same thing as 10,000 square meters. 10,000 square meters, this is 1 hectometer times 1 hectometer. If we look back at our table here, meter would be right here, hecto would be 100 times bigger than that. So this is 1 hectometer times 1 hectometer, which is the same thing as 1 hectometer squared. So a hectare matches up with a hectometer squared. That's how I want you to remember that for me. So hectare is very similar to this. A hectare, I did the calculations, it actually ends up being 107,639 feet squared. So it's a little more than twice as big as an acre. So a hectare is bigger than an acre. But these are things we should know. These are things that match up in a similar way. So things measured in inches squared in the US would be measured in centimeters squared generally in metric, and so on. So let's move on to our next example here. Let's think in the same way as we started with length. We're going to be thinking of the most appropriate measurements for things in area. Let me get rid of this a second. We don't need this right now. So determine what's most appropriate to measure the area of and then we'll have 5 things again like before. Determine the area of a penny. I'm kind of saying the surface area, the side area of one surface of the penny. Would you use meters squared? I sure don't think you would want to do that. I would probably use centimeters squared or even millimeters squared. I think millimeters squared would probably be the best one though, so I'm going to put millimeters squared. This I would measure the radius most likely in millimeters, and then so I could find using pi r squared, we'll get to that later, but using pi r squared I would find the area of the penny, the surface area. How about a footprint? So over here in the sand, hopefully you've had the chance to visit the beaches at some point in your life here in Southern California or elsewhere. I know the beaches in Hawaii were spectacular. Some of the beaches in Michigan are quite phenomenal too, along Lake Michigan, along some of the other Great Lakes. But a footprint, I think what would be best for that would be not millimeters squared. I think that'd be a little too small. You could measure things in centimeters squared here. So centimeters squared for a footprint. Part C, how about this? An in and out parking lot. So an in and out parking lot. One of my favorite restaurants in California, especially fast food wise. I just feel like they got good fresh ingredients and the burgers taste amazing. Okay, yes they do. And in and out parking lot, what would be best for that? I think centimeters would be a little too small. I think meters squared would probably be the best way to go there, the more common ones. We generally don't use decimeters squared or decameters squared or hectometers squared, except if we're doing hectares, then we would use hectometers squared. But generally it's going to be millimeters, centimeters, meters, and kilometers are the 4 most popular ones that we use. How about this cute little guy, girl, I'm not sure, but how about a snow angel? Aww. Aww, they're so cute. Aww, okay, so a snow angel, maybe you've never made one since a lot of you have rarely seen snow, but hopefully when it snows you get out there, you have fun with it. If you're from Michigan like me, we make snow angels like every day where we can for about 5 months straight. But snow angels here in where we live, Quartz Hill, Lancaster, Palmdale area, not so many opportunities to do that. But I would say what would be best, probably centimeters squared, maybe meters squared. So I'll put centimeters squared. I think is the best one, especially with a little baby like that. I think centimeters squared would probably be best. So centimeters squared or maybe meters squared. So I'll put both of those as viable options as being most appropriate. And then how about the area of, you've never visited here, don't be afraid by the name. It's pretty incredible. You should go visit Death Valley National Park. Maybe not in June, July, and August though, because they've had some pretty insane temperatures there. Death Valley National Park, I think, would be best to measure in kilometers squared. Maybe hectares too, but kilometers squared I think would probably be best. Let me erase that a second. So kilometers squared, or I'll put HA, or the hectares. Remember, hectares is already an area unit, so we don't put hectares squared. If you put HM, then you would say hectometers squared, but a hectometer squared is a hectare, so we leave the squared off of there. And I felt like I just couldn't let this go, so the highest or the hottest temperature ever recorded in the world, maximum temperature, was 134 degrees. It used to be Libya at 136 degrees, but they deemed that temperature measurement invalid. I don't know why. So this now has become the world record for temperature. So 134 degrees, probably not the best time to visit in the summer months. Also here, this is interesting, July 12, 2012, the mean 24-hour temperature, so the average 24-hour temperature, talking throughout the entire day, was 117 degrees Fahrenheit. So it's like at least 100 degrees in the dead of night. Dang, that is hot. All right, so There we go. Death Valley, great place to go visit, but maybe consider doing that in the spring, fall, or winter months. Really cool sand dunes, all kinds of cool things to go see in Death Valley National Park. So let's work on another example though. So how many times larger is 1 kilometer squared than 1, let's see if you remember what this stands for, dm, so 1 dm squared. If you say decimeter, you're correct. If you said decameter, you are not correct. Decameter, remember we have the dA and then the m, and so decimeter is just the d. So dm, decimeter squared. Which one of these is bigger? Is a kilometer squared bigger, or is a decimeter squared bigger? So I look at this, and kilometer is the top dog up here. How many times bigger in terms of just the distance is it? So it would be 10, 100, 1,000, 10,000 times bigger than a decimeter. So if I draw a picture, that's going to be very helpful for this one. I'm not going to draw this one to scale or anything. I'm just going to draw a square as best I can freehand. And it's not too bad with this tool that I'm using here. So I'm pretty happy with that square. I'll say 1 kilometer by 1 kilometer. That's the same thing as we just determined it was 10,000 decimeters by 10,000 decimeters. Remember, leaving a space instead of a comma for 5 digits or more. So if I multiply 1 by 1, that's 1 kilometer squared. But if I multiply 10,000 by 10,000, what does that become? 10,000 times 10,000. That's 1 times 1 is just 1, and then you have 4 plus 4 more zeros. This becomes a 1 with 8 zeros after it. So when we're using spaces instead of commas, I think it's a good idea to kind of work backwards. So let's write down my 8 zeros. 1, 2, 3, leave a little space. 1, 2, 3, leave a little space again. And there's 7 and 8, and so I've got a 1 in front of that. This is 100 million times larger than. 100 million times larger. And that's a lot, so I'm going to put an exclamation point. That's a big difference. So notice a kilometer was only 10,000 times bigger in terms of just the distance, but when we take that times that, we always are squaring these values. So if we go back to here, this was 2 times bigger meant 4 times the area. We squared 2. 2 squared is 4. Here, instead, we're squaring 10,000, so it's 100 million times larger. Let's also think of here some area formulas now. So these are some formulas you need to know. We've already done some with rectangles, or squares are just special types of rectangles. We've been doing some squares there. You can say a side squared for a square. It's the same thing as base times height though. So you can say that, or some textbooks will say length times width. Depending on the situation, you might say length and width instead of base and height, but they mean the same thing. A parallelogram, I feel like, is one you should know as well. And that one is also base times height. And oh man, like magic, a parallelogram appears. Disregard this line for right now, but this would be a parallelogram. And so why is this the same as a rectangle? You don't have to draw this. This is just kind of for your information. Watch this though. I just cut off a triangle part of this parallelogram, and I'm just going to move it over here. And just like that, boom, I now have a rectangle, which is base times height. That's why these are the same. Now if we think of next a triangle, a triangle is 1/2 base times height. And oh man, just like that again, we got this rectangle, base times height, and I see 2 triangles there. So if I split up the triangles, this is an easy way to remember. Again, don't have to write this down or draw these pictures. Just a way to remember though that, okay, this was base times height, and then I split it into 2 triangles, and each one would be 1/2 of that, 1/2 base times height. simple way to remember these formulas without really memorizing them, I think. And then finally, just for right now, this is the last one I want you to know. You'll have to know some more later on, but circle pi r squared. We're not going to break that down as to why that's the area right now, but that can be proved as to why that works out as well. So we're just going to remember pi r squared. If you memorize base times height, these other ones should be easy to derive from there, based on the pictures we had just a moment ago. So let's continue with what we got here. So we're going to use those formulas at this point, one of those formulas for this next problem. Find the area of a rectangular driveway with length meters and width 4.5 meters. Now, you may have noticed some stuff in this chapter. I hope that you're really saying, hey, Mr. Wagner, this stuff I could actually use in my everyday life. And I'm saying, yeah, you really could. This is kind of cool, right? Some of these other things I've been learning, and just math in general in the high school curriculum, Algebra 1, geometry, things that you learn there, are you going to use that stuff in your particular everyday job? Probably not, all right? If you become me, yes, you're going to use that as a math teacher all the time. If you become maybe an engineer, maybe an architect, maybe certain other things, you're going to use these ideas all the time, but are you using the thinking process? Are you getting better at thinking with these other things? I sure hope so. But with this stuff, what we're doing right now, this is so practical. This is awesome. I'm really excited that we're going over this and that you have the chance to learn this, because what we're learning right now and what we're going to be learning for these next couple chapters, extremely practical stuff that you can utilize every day of your life, especially as we convert more and more to the metric system. I hope we'll need to be thinking of things like this a little differently. So the area, I would say you can use either base times height or length times width. They give me the words length and width, so I'll use the LWA instead, but it means the same thing as base times height, and it's already there for me. I just plug in 70, I plug in 4.5, I get out my calculator, and I do that. You might be able to do that in your head, but it might be a little tricky one. And this would be 315. Like, I could have done 70 times 4 is 280, and then half of that is 35, and added those together to get 315. But 315 is our answer. This would be in meters, not just meters, but we just multiplied meters times meters. 70 meters times 4.5 meters, therefore it's meters squared. It's an area always in a units squared. Okay, so that's a pretty easy example, I hope. But example 5, this one will be a little bit trickier. Maybe you've flown in a plane before, you looked out your window and you saw stuff like this. I think the reason for this, is best I know, is that they have these like circular sprinklers that have this point right here where they just kind of rotate around that point, and it makes it easier for them to water all their crops and whatnot. That's my best guess. It's not an alien formation. I think that's why they do that. I think that's what they have that like that for. And so we're going to find the area of a circular field if its diameter is 1.5 kilometers. So that's pretty big. That's almost a mile if we go back to a little bit more. There we go. If we go back to this, 1 mile is 1.6 kilometers. So 1.5 kilometers would almost be a mile across. So that is a very large field. This might be something, there we go, this might be something like a mile by a mile road, if you had one big one, if this was a mile by a mile, and one big one would be 1.5 kilometers approximately across for the diameter. So what's our formula? Let's look back here, and this one's a circle, so we should be using pi r squared. Pi is about 3.14, but we'll talk about more with that in just a second. But the radius is what we need for the equation. So the area is going to be, yep, like that, so I'll keep that consistent. The area is pi r squared, and I'm going to plug in, I'm going to keep pi as pi for right now, and I'm going to make an error. Let's see if you can check out my error here. I just made an error. What did I do wrong? I didn't notice this word right here, diameter. The diameter is 1.5, so I should be taking this and plugging it in here, but dividing it by 2 first. So diameter is 1.5. You'll notice I just drew that in a different color. I want you to do the same thing. So if you don't have a different color right now, pause the video, go get one, come back. Okay, did you come back with a different color? Alright, you got that. Let's do the stuff in orange as I continue through this. Anything in orange should be in a different color. So I want to take this now and erase what I got there. This would be now 0.75. If I divide 1.5 divided by 2, I get 0.75. Now if I plug that into a calculator, let's take out my calculator again, 0.75 squared is 0.75. 0.75 mean the same thing. So that times itself would be, I'll write that in here, 0.5625. And I want to multiply this by pi. If you use 3.14, it gives you an approximate answer. But if your calculator has a pi button on it, like mine does here, you should use that instead. Unless it specifically says to use 3.14, use the pi button on your calculator. It will give you a better answer. You'll notice when I type in pi, my computer has pi memorized to all these digits. Pi is an irrational number. It means it never stops. It keeps going and going, so it doesn't actually stop right here either. And it never repeats. There's no real pattern to the digits. So 3.14 is a good approximation. 3.1415 is a better approximation. 3.14159.265 is how far I have it memorized. That's a even better approximation. But type it in as pi in your calculator. It'll give you a much better answer that way. And let's round this off. Generally, I'll have you round off to 2 digits unless I tell you otherwise. So let's round this off to 2 digits there. It was 1.76, but the next digit is 5 or higher. When that's the case, we round up. So we're rounding up to 1.77. This is kilometers. I multiplied kilometers times kilometers with the radius squared, so that's kilometers squared. About 1.77 kilometers squared. Pretty big area for the circular field in question. And let's draw a picture. I meant to draw this a little earlier, but let's draw a picture to go along with this, just so we're aware of what was what here. So this was all the way across was 1.5 kilometers. In your different color, I'll take out my orange here, we divided by 2, so this was 0.75 kilometers for the radius here. That's another radius right here, 0.75 kilometers here. So from there, from the center point to any point along the circle, you're going to have 0.75 kilometers. Make sure I see these different colors in your notes, otherwise you'll miss out on some of the points for the notes. It makes it a lot easier to understand later when you look at it. So now, finally to volume, our last big topic heading. Put another topic heading, volume, and then let's write this down. Volume is, in a similar way we defined it here for area, it's the same sort of thing, but it's the space enclosed by an object in now 3 dimensions instead of 2. Space enclosed by an object in 3 dimensions. And what kind of units do we use? We use units times units times units, which would be cubic units. Cubic units. That eye looks a little funny. There we go. Cubic units. Right. And so I'll just make this consistent, I guess. So we should say, I had it this way before, we use cubic units now. Okay, so we've got, now instead of drawing this exactly, I could take out my ruler again, but this one I'm not going to draw exact or precisely. You could if you wanted to, if you want to get that extra practice, but I'm just going to kind of eyeball it here. So I'm going to say that's about 1 centimeter by 1 centimeter for the front, and let's write that in here. You know what I could do? I'm going to do this instead. Clever, clever, Mr. Wagner. I'm going to erase this. I'm going to go back here and see if I can do this. I'm just going to copy and paste what I drew over here. You can't do that. I'm sorry, but I'm going to do that here. And so I'll pause this and do that in just a second. Oh, Mr. Wagner, that was cheating. That was slick. That was fancy. I'm sorry you can't do that, but okay, I'll give you a little moment here to do your 1 by 1 square. And so 1 centimeter by 1 centimeter. This one is 2 by 2. And now we're going to kind of project it back this way. So we're doing a 3-dimensional picture as best we can. This, I'm just freehanding this part. So this, I'm going back, and I'm saying that part going back was also 1 centimeter. And then here I'm going to try to do the same thing with this one. I'm projecting it back 2 centimeters. So basically this is how, I know some students struggle with drawing 3-dimensional boxes like this. You can draw the box first and then go back like that. Another way some students do it, this, you don't have to draw this up here, but this is another way you could do this. You're using pencil, it works really well like this too. You can draw a square and then another square kind of behind it like that. You connect the dots. Come on, it's skipping, I don't know. And then you can just take an eraser and erase the little parts here. Erase that there, and you have a very nice cube as well. So you can draw it that way too. That also works. I'm going to get rid of that though and just go with what I have here. So this is 2 centimeters by 2 centimeters by 2 centimeters. And so what's the volume of this one? The volume of this one would be 1 by 1 by 1, which is 1 cubic centimeter. So this is 1 centimeter cubed. This one though is 2 by 2 by 2. So if you just say, oh, this one's 2 times bigger, not true at all. This one, the area was 4 times bigger, and now the volume is going to be 8 times bigger. 2 times 2 times 2 is 8 cubic centimeters. So the main thing to notice here, if you go 2 times bigger, sides, sorry. 2 times bigger sides. So each of the sides you just multiplied by 2 from here to here. That would mean 2 times bigger sides means you actually have 8 times bigger volume. It's the cube of whatever you multiplied by. So if this was 10 times bigger, this would be 10 times 10 times 10, which would be 1,000 times bigger volume. It gets pretty crazy. The bigger you go, the faster the volume expands. It's a cubic type of expansion here. And so from there, let's fill in a similar table to what we had with the area. So we'll put US customary right here, and then over here we'll put the metric alternative. I would say equivalent, but it's not exactly the same, but it's an alternative that is used instead of what you see here. So this would be inches cubed would be a US customary way to say volume. You could also see things like ounces. This would be more of a liquid measurement, but ounces, cups, pints, quarts, and even gallons. You would see that a lot. Metric alternative or alternatives would be cubic centimeters. Inches and centimeters are kind of the same in a sense. They're like metric US buddies, you could say. And before I do that, cubic centimeters, sometimes you also see it listed as CC, cubic centimeters. So that's something we'll need to remember. And you also see things like liters. I'm going to show you what the rest of the world uses to spell liters. They usually spell it like this. So if you see that in a foreign country, this just means the same thing as liters. As far as I know, we're actually the only country that spells it like this. So again, even when we use the metric system, we're still stubborn. We're not going to spell it like the rest of the world. We're going to spell it like how we want to spell it, right? Right, okay. So liters, same thing there. And instead of feet cubed or yards cubed, in the metric system you might see meters cubed. This is more with solid materials, so I'm going to put solids next to that. And you might see kiloliters. Kiloliters is a measurement that's already in volume. A liter is a measurement of volume, so I don't need to put liters cubed. That wouldn't make any sense. So kiloliters, that is when we're measuring liquids. So meters cubed, cubic meters, so when we're doing solids. Kiloliters or liters is more when we're doing liquid type measurements. So these are going to be more solid type measurements. These are more liquid type measurements. There's an exception with cc's. We'll get to that later though. So let's go on to our sixth example and write this down for me. So determine what's most appropriate to measure the volume of these things. So let's start off with a container of juice. Terrible T there. A container of juice. What would be the best way to measure that? I think you could say that this might be a little more than a liter. So I think a liter would work. I think milliliters would also work pretty well. You might see both of those things labeled on the side of a juice bottle or a water bottle or some sort of bottle. So milliliters or liters, both those things would work. Stop skipping on me, pen. Come on now. There you go. Choice B. Letter B. Part B, I should say. A dump truck full of, this looks like I got some wood chips in here, so a dump truck full of wood chips. I've done some landscaping projects before and I've had to calculate stuff like this. I figure out, okay, how much do I need to buy, and they would usually sell it in the US in like cubic feet or cubic yards, but if you're doing this in a metric way, cubic meters would make the most sense. This is a solid measurement, so we wouldn't use liters, we would use the cubic meters. Think of it like that instead. How about a go-kart engine? Oh, now that makes sense. If you've ever played one of the greatest games in the world, Mario Kart, you'll notice that you can do either 50cc, 100cc, or 150cc races. This is a 150cc engine. That means 150 cubic centimeter engine. So this you could think of in terms of centimeters cubed, or you could think of it in terms of cc, cubic centimeters, means the same thing. So that I think would be the best way to think about the size of a go-kart engine, cubic centimeters, centimeters cubed. How about this, water flowing through, and if you know what this is right here, maybe you've been there before, water flowing through Hoover Dam. So I would say liters probably be a little too small. There's probably more than 1,000 liters flowing through there, so I would say kiloliters would probably be your best option, but depending on the day, maybe they're not going to let too much water through on a specific day. I think kiloliters would probably be best. Liters might be a good alternative too, so I'll put both of those down. And then the volume now of a dime. What would the the area of a dime is different. A dime has volume, Mr. Wagner? Yeah, look here. This is a stack of dimes. This stack of dimes definitely has volume, so that means each individual one has some volume too. It's not very big, but it has volume. And so I think the best way to measure that would probably be, you could measure the area of that and then multiply it by the thickness, but I think the best way to think about that would be in millimeters. So millimeters cubed, cubic millimeters, for the volume of a single dime. Let's move on to some more formulas here. So volume formulas, these are three that you should know right now. These are three you should get memorized. The rectangular prism, that's just a fancy way to say the volume of a box. Okay, so just think of a box when you hear rectangular prism. It's length times width times height. You probably knew that one already, but if not, there it is. A right cylinder just means, the word right in front of that just means it's going straight up and down. It's not on a tilt at all. So a cylinder has a circular base, pi r squared then for the base, multiplied by the height would give me the volume for that. So circle times the height. Area formula times the height gives a volume for a right cylinder. In a sphere, this is one you're just going to have to kind of memorize. I don't have a fancy way to remember this. But 4/3 pi r cubed, you may have to use that equation. That one takes, as far as I know, the first time I really learned why this was what it was, I had to know calculus to be there. So we can use calculus to prove this formula. But if you're watching this video, you probably have not learned calculus yet. So just write that down and say, hey, that's what it is. I know somebody in calculus could prove it to me, but I'm just going to accept it right now as true. So metric equivalence, these things match up with these things over here. So I'm going to have some cubic measures of length over here, and then I'm going to have their liter equivalents over here. So 1 cubic centimeter, 1 cc, is the same thing as 1 milliliter. 1 cubic centimeter, that's pretty small. So that was like what we had back here. That's a pretty small little volume here. 1 cubic centimeter would be like that, kind of like that big. 1 milliliter matching up with that. If you have 1 decimeter, 1 dm cubed, that's the same thing as 1,000 cubic centimeters, because this would be 10 centimeters by 10 centimeters by 10 centimeters, which would be 1,000. So this is 1,000 cc, which would be the same thing as 1,000. 1 cc is 1 milliliter, so 1,000 cc is 1,000. Oops, 1,000. Not 100. 1,000 milliliters. And 1,000 milliliters, if we look back at our basic metric prefixes table, 1,000 milliliters would be the same as, going up 3 here, 1 liter. So going to 1 liter. So 1 decimeter, we usually don't say a decimeter cube, but that's what this equals. It's 1 liter. And then going up from there, one more, centimeter to decimeter to the next one would be 1 meter cubed. 1 meter cubed is the same thing as 1 kiloliter. And now I want you to get that different color out again, just to kind of differentiate this. So from here to here, it was times 1,000. It's 1,000 times bigger. A milliliter to a liter is 1,000 times more. And then the same thing from a liter to a kiloliter is 1,000 times more. So if you went all the way from here all the way to the end here, this would be times a million, times 1, put a little space, 3 zeros, put a little space, 3 zeros. So times a million if you're going from milliliters to kiloliters. We're having that, I guess I should say, times a million if we're going from kiloliters to milliliters, it would be 1,000 times or a million times more. So think of it like that. So let's do another example here. We are going to find the volume of the figure. We're going to just freehand a figure here. If you want to use a straight edge to draw a better picture, you can. Otherwise, just try to freehand it as best you can. So I'm going to draw basically a box. So I'm going to draw a rectangle, and then you could draw another rectangle behind it and connect the dots and erase stuff, or you can just kind of go back a little ways like that, go back at the same angle over here, so all these angles are going back the same way, and then connect those 2 points there. And let's call this 100 centimeters down here. 100 centimeters, 1 meter right there. This is 40 centimeters this way, and this is 30 centimeters this way. So what's the volume of that going to be? Well, I look back at my volume formulas if I forgot. And this one's just a box, so length times width times height. So I'm going to write that equation down and plug in the numbers. My length, that's 100. My width, I'll call it 40, and my height 30. Does the order really matter if they're all being multiplied together? No. So you could flip-flop the order here. If they're all being multiplied together, it doesn't make a difference in the end. I'm going to do 1 times 4 times 3. That's 12. And then I've got 1, 2, 3, 4 more zeros to add to that. So I'd have 1 0 here, a little space, and then 3 more zeros. So this is 120,000. This would be centimeters times centimeters times centimeters. This is a volume, centimeters cubed. That's one way I could think about this. But I can also think about this, 1,000 centimeters cubed, 1 cc, 1,000 cc here is the same as 1,000 milliliters, which would be 1 liter. So if this was a solid unit, going back here, if this was a solid thing, I would keep it like that. But if it's a liquid thing, I'm going to change it to liter. So it kind of depends on the context of the problem what your answer is going to be. If it's a solid, more of a solid type measurement, I would leave it like this, or put that in meters cubed. But this is going to be less than a meter cubed, because remember, we're supposed to be multiplying by, if we're going from centimeters cubed to meters cubed, we go times 1,000. It's a million times bigger that way. So I'm going to leave this in terms of cc instead. So you could say this, or that many cc, or I could take this and say that is, coming back here, 1,000 cubic centimeters is the same as 1 liter. So this would be the same as 120 liters. And I did want to write one other thing first. Oops. I wanted to write 120,000. Since 1 cc is the same thing as 1 milliliter, I can write it like this, or I could write 120 liters right there. Okay, so this would be my final answer. What different context might we have? It just depends on the context here. So let's put in our different color, let's put a solid up by this top one. Write that down for me. This would be more of a liquid measurement. So if you were using a liquid measurement, that might be something like your fish tank. And this is the world's awesomest fish tank. This is the beginning of, well, this is level 1 basically of Super Mario Brothers, and then some of the end stuff in level 1. But maybe your fish died, so this would be more liters or milliliters in the fish tank. Maybe your fish died though, and so you dug a hole. How much sand or dirt would you need to fill that hole? That would be more of a cubic centimeters measurement. So that would be more of a solid measurement. How much dirt would you need to fill the hole back in? Poor Hemingway. I can't read this. I'm so curious what this actually says. But Hemingway, the fish, is dead here. He lies here. He was the first fish something passing. I don't know. Maybe you can tell me what that says. Let's do another example though. If you are in the health careers type profession, you will be using metric units for measurement a lot. I am not doing example 1 like example 8 in the book. That is on page 444. So if you want to look at that page right now, that I would highly recommend doing that. But I feel like you can just look at the example in the book on that one, and in the context or in kind of addition to what we're doing here, I think a problem like that will make sense when you get to it. But look at example 8 in your book if you need a little extra help with determining what the most appropriate answer might be for a certain type of volume measurement. But this one we're going to skip ahead to one like this. This is more similar to example 9 in your book. But let's write this down right now. I don't want to use orange. I want to use black right now. Here we go. A nurse Oh, I got you, Mr. Wagner. We got some nurses over here. So a nurse must give a patient's 5 cc, so 5 cubic centimeters. cc is most often used in health type careers where you have to give a certain dosage of a drug or something like that. So 5 cc of a drug in 600 cc of, and what is this right here? This is an IV or an intravenous fluid. So intra going inside your venous parts, your veins, so intravenous fluid. And we'll break this into 2 parts. So how many milliliters of the drug is this? And before you're starting to say like, oh, that sounds like a really tough problem, I don't know if I can do this, remember 1 cc is the same thing as 1 milliliter. This is perhaps the easiest problem we've done so far then. So 5 cc is the same thing as 5 milliliters. You can just remember cc and milliliters go together, you got your answer. It's 5 milliliters right there. Since 1 cc is 1, 5 cc is going to be 5. And then part B, what is the total volume to be administered intravenously? I think that's a word, intravenously. I'm pretty sure, but if it's not, sorry, we're just going to use it here. I just coined a new word then. But what do I say here? Well, you're going to have 600 milliliters, or 600 cc, in other words, of the IV fluid to start. You're going to be adding 5 cc, or 5 milliliters, of the drug to that 600. So all we need to do here is add 600 plus 5, and we're going to have 605 cc, or you can say that's 605 milliliters. So both of those would mean the same thing. And then there's a problem in your book. If you look at page 445, if you're interested in a health career profession, maybe being a nurse or a doctor of some sort, and you might have to give an IV or a shot someday, look at the problem there. An interesting problem. See if you can answer that without looking at the answer. So check out that problem at the bottom left-hand corner of page 445. I think a pretty interesting problem there. But example 9, our final example for right now. Just kidding, our second to last example for this lesson. I want to bring up something you might recognize, especially if you're in my class right here. Okay. Hey man, I might know that guy. I don't know. Where are we? We are at Quartz Hill High School. Alright, so very good. So we're going to exit Street View. This is Google Maps. If you've never used Google Maps or kind of played around with it, it is a pretty awesome program. You should check it out sometime. There we go. So now I am looking southbound. This is north right here. And so I'm zooming out a ways there. And I'm going to be heading on over here to this area. Oh, what is all this stuff here? That looks interesting. What are these things right there? I want to zoom in on that a bit. And there we go, zooming a little closer. I'm going to go to Street View here, so I'll put my little guy there, and let's see what I'm looking at, or what I wanted you to look at right here. I'm going to turn around. The Quartz Hill water towers. Okay, so we're going to, I didn't actually go there and measure these things, but I'm going to pretend like I did, and I'm going to pretend like this is what I found the measurements to be. So we're going to say a water tower is in the shape of a right cylinder. Suppose, again, I did not go measure this. Maybe I'll have to do that one of these days. I'll actually go measure the water tower. But suppose it has a radius of 5 meters and a height of, I don't think it's actually this tall, but I'm going to pretend like it's taller than it is, of 22 meters. I look at that, I don't think that's quite 22 meters, but maybe it's 5 meters for the radius. We're going to pretend like it's what I have here. Height of 22 meters. And the question is, what is the capacity in liters of the water tower? And that's my question to you. So let's draw a water tower here. Basically draw a half circle, but more of an ellipse type shape. And then we're going to make this going straight up here. So it's kind of looking at it on an angle, and then draw another circle up here, but it looks more like an ellipse because we're looking at it at an angle. Okay, and so something like this. We've got, let's label the parts that we had given to us. This, I'm going to make some dashed lines here because that's the rest that we couldn't see. This right here is 5 meters, and then the height of it is 22 meters. So based on that, what's my volume formula again for a right cylinder? In case you forgot, go back in your notes, and we're going to use this one, pi r squared times h. Why does that work? Well, it's just the circle, which is pi r squared, and then we're just multiplying that by the height. It's the same circle going all the way up. So if we do pi r squared times h, that'll give me the volume of the whole cylinder. And so we have pi. I'm going to leave that as pi for now. My radius is 5, so I'm going to do 5 squared times 22. And I would want to do my exponents first here, so this would become 25. And then from there it's all multiplication, so the order no longer matters. So it's all multiplication. 25 times 22 is 550. So I have 550 times pi would be my answer. Let's not use 3.14 because we have a calculator with the pi button here. So 550 times pi, that'll give me a better answer. That's about approximately 1727.8. If I round that off to 2 digits, this 5 would go up, or I mean this 7 would go up to an 8 because this is 5 or higher. So I have 727.88, 1727.88. That is in meters cubed. Now it says, what's the capacity in liters instead of this thing? So remember, we go back here if we need to, and we look at this. 1 meter cubed is 1 kiloliter. So 1 meter cubed is 1 kiloliter. Let's write that down here. This would be the same thing then as 1727.88 kiloliters, but I want my answer in liters instead, it says. So this, I'm going to need to multiply this by, if I go back to liters, I would have to multiply this by 1,000. I'm going to have to move my decimal 1, 2, 3 spots there. And so I think it's best to probably write the number backwards so we have the spaces in the right spot. 1, 2, 3 would have an extra 0 right here. So I'm going to start with that 0, write an 8 and an 8. Then I've got my space, and then I've got a 7, 2, a 7, and then another space, and then a 1. So this would be that many liters. That's a lot of liters, but that's why we have water towers. We need a lot of liters in case we run out of water to supply people with. So let's now move on to what is my final example here. So this one I'm going to break into 2 parts again. It's about how many times larger is a cubic meter, a meter cubed, than a dm cubed, a decimeter cubed. So with this one, think about how we did this with area first. Think about, we did a similar problem with area. Not quite there yet. Where is it? There it is. Okay, so we did 1 by 1 kilometer, the same as 10,000 by 10,000 decimeters. We're doing the same sort of thing here now, just with volume. And so let's draw a picture. We'll just go freehand on this one, but we're going to draw a cube. Which one's bigger, meters or decimeters? Meters, if you say meters, you're right, that's bigger. So I'm going to go 1 meter by 1 meter by 1 meter. And then over here, this is going to be but how many decimeters are in a meter? Go back to here, and then we'll go, that's just 10 decimeters in 1 meter. If I go back this way, it's 10 decimeters in 1 meter. So I have 10 dm here. But that doesn't mean it's 10 times larger. Remember, we have to multiply 10 by 10 by 10. So what is the actual answer going to be? It's going to be, we have volume is length times width times height, and this is 1 by 1 by 1 would be 1 meters cubed, but 10 by 10 by 10 would be the same thing as 10 cubed, so I could just write it like that. 10 by 10 by 10 is 1,000 times bigger, so 1,000 times larger. Remember, with 4 or less, we don't need the spaces, so it's 1,000 times larger. Exclamation, that's a lot bigger than I was originally thinking. Maybe not what I was originally thinking, maybe what you were. Much bigger. Remember, volume, the bigger things get, the exponentially faster they grow when we do volume instead. So let's do one more here. How many times bigger is a cubic kilometer? Oh, sorry. Hectometer. Cubic hectometer than a cubic millimeter. So hectometer was feeling kind of left out and felt bad for it, so I had to put that in here. Before I show you that one, this one was more like, okay, an Nalgene bottle or something like that. That would have a volume of about 1 liter, which is a decimeter cubed, and then a big old barrel would have a 1 kiloliter volume. So you could pour 1,000 of these into a kiloliter barrel. A kiloliter barrel is going to be quite large. So this is not to scale by any means, but just think of that. I bet you'd probably draw a little Nalgene like this on here. It'd probably be about this big. It'd be like, oh well, that's in black. That's okay, and you could fit 1,000 of these things into here. And so with this other one though, a hectometer cubed to a millimeter cubed. A millimeter cubed is very, very small. I would say that's something like an eye drop. So the amount of liquid in one single eye drop, that could be something comparable to a millimeter cubed. How many times bigger though is a hectometer? So let's draw another box, and we know the hectometer is bigger, so I'm going to put it along the sides here. Not my best box there of the lesson, but it'll do. 1 hectometer here, here, and here. So how many times bigger is a hectometer than a millimeter? We have to go how many spots up or how many spots down? We're going 1, 2, 3, 4, 5 spots. So this should be times 10, 100, 1,000, 10,000 times 100,000. So it's 100,000 times bigger than that. So I'm going to put 100,000, use a space instead of a comma. 100,000 millimeters is the 1 hectometer. And so rather than writing 100,000 3 times, I'm just going to say that one's 100,000 millimeters, that one's 100,000 millimeters, and that one's 100,000 millimeters. 1 hectometer is equivalent to 100,000 millimeters. So that's what all those 3 things have to be. Again, volume is length times width times height. Since they're all the same, I can just multiply 100,000 times itself 3 times. And so originally you might have been saying, oh, it's 100,000 times bigger. That's a lot bigger. Whoa. Hold up. Not even close. Not even close. This is 100,000 times itself 3 times. So we have a 1, and then 5 zeros times 5 more zeros times 5 more zeros. That would be 15 total zeros. So I'm going to erase this 1, work my way backwards. I have 15 total zeros here. So 1, 2, 3, a space. 1, 2, 3, a space. 1, 2, 3, another space. 1, 2, 3, another space. 1, 2, 3, and another space, and then finally my 1. So that's 15 zeros. This is 1. What do I even call that? This is 100,000 here. This is a million. So this is a billion, and this is a trillion. Do you know what comes after trillion? If you've never heard of it before, I wouldn't be too surprised. I just learned this a couple years ago, actually. After a trillion, you have 1 quadrillion. So this is, let's rewrite the 1 with 3 zeros, 15 zeros, using spaces. So this becomes, I don't need to rewrite this stuff, sorry. I feel like we did this work already here, so I'm just keeping it the same as I had up there. So it's 1 quadrillion times larger. Crazy. That's cray-cray. That is crazy. 1 quadrillion. That's how you spell that. So 1 quadrillion. Box that in. So what's a good comparison? I don't know if this is a perfect comparison, but this is just what came to mind. So a little eye drop compared to a rushing, gushing waterfall. There's just a ton more water. I shouldn't say a ton even, because that has a very specific unit. Just an incredible amount more of water in the waterfall compared to an eye drop. So just a crazy amount more here with that. So hopefully you found that helpful, useful, and practical. I think lots of great things we learned in here. Kind of a long one, sorry about that, but there was just a lot to cover. So hopefully you found all that useful. Go back and review the lesson if you need to recap anything or to hear anything again. And I will see you guys later.